So today we have our last class about energy and everything related to energy, and it's called efficiency and power. So we're going to look at these two concepts that are new for you guys probably. So before we start, I wanted to remind you of a couple of equations that will be useful today. One of them is the equation for work. So work was defined as a force times a distance. So we're going to be talking a little bit about work again today. And work is basically a useful type of energy because it is talking about a force that is able to move something through a distance. So work is something useful that we want. And another equation that we saw ages ago, but that can be helpful today, is the equation for speed. So speed was distance over time. When we have a constant speed with no acceleration. So these two equations we'll be using in a second. But first I wanted to get to the concept of efficiency. So efficiency, maybe you've heard before, is also used a lot in normal life as something that is able to do a lot of work, or someone that is able to do a lot of work putting in not that much effort. So it's basically how much you can do with what you have. So the way in which this is represented physically or mathematically in physics is through the following equation. So we have efficiency, which is going to be equal to, so what we want to see with efficiency is how much useful energy we get out of a machine or something that we have to put energy into. So how much of that energy that we spent on making the machine work is going to be actual energy that we can use for something. So efficiency is defined as the useful energy. So it's a fraction of the useful energy that you get out of the total energy that you put into it. Right? And it's generally given as a percentage because this is going to give a fraction or a decimal. So because it's usually given as a percentage, we can multiply this division by 100% so that we get a percentage out of 100. So an example of this could be, maybe you're thinking, like, where is this represented? So maybe we're talking about a water heater. So we have to connect a water heater. Maybe you've seen them. You connect them to the wall through the cable. So it's this like pot that heats up water. I'm not very good at drawing, but let's say it looks something like this. So inside it's filled with water, right? And it's gonna heat up the water by being connected to the wall through a cable. So maybe you need to put in, let's say 1,000 joules of energy through the wall, and it's gonna give heat to the water, and the heat is a type of energy, but maybe it only gives, I don't know, 300 joules of energy to the water. So out of the 1,000 joules that you had to put in for the machine to work, only 300 joules of those were useful, and the rest were lost in the process, right? So in this case, the efficiency of this machine, maybe efficiency would be the useful energy, which was the 300 joules, over the total energy that we put into it, which was 1,000 joules, times 100%. And if you put this in your calculator, this is going to give you 0.3 times 100, which is 30%. So this water heater in this example has an efficiency of 30%. And the truth is, no machine is 100% efficient. So that's really important. Let me write that down. No machine can be 100% efficient. That is actually a rule in physics, a law that has never been proven otherwise. So many people want to invent these machines that can work forever, that the same amount of energy that you put into it goes out as useful energy. Imagine, like, the person, if someone discovers this machine or is able to construct it, they would become rich and famous and would make a lot of money because they're not wasting any energy. All of the energy that they put into it is useful. So many people have been trying to test this law and find a way to go beyond it, but it has been impossible. Why? One of the reasons is because the real world has friction. We've seen this a lot. There's friction. So in any machine, anything that is moving, even if we're talking about electricity going through a cable, it's going to feel some friction and it's going to slow down. So some of the energy will be lost in the cable, right? So friction is one of the most obvious reasons why machines are not 100% efficient. Most of this energy is lost as heat. So most of this goes out as thermal energy. I don't know if you remember from the skateboarder, thermal energy, that once you put friction on the ground, he lost some of his energy to heat because of friction. So this is what happens almost always. A machine that works, let's say you have an elevator. That's another example. You have an elevator. How do you draw an elevator? And the elevator goes up and down, and it requires this giant pulley system to work, and it requires a lot of energy, and it requires electricity, and it's going to be converted into some useful work. The force of gravity pulling it times the distance that it travels. That work is going to be the useful energy, while the total energy is the energy you put into it when you connect it to the electricity. And the elevator will have friction in its cables with the pulley, and it'll get hot. Probably the cables are very hot because of the friction as they move through the pulley. So a lot of energy will be waste energy as friction because of friction. So this is waste energy, and only some of it will be useful energy. So in this case, for example, if 1,000 was the total energy, how much energy was wasted if only 300 were useful? Well, 1,000 minus 300, the total energy minus the useful energy, will give you a waste of 1,000 minus 300, 700 joules. Right? So the waste plus the useful has to equal the total energy, of course. And what you want to do when you're building a machine is to reduce this waste so that the useful energy will increase, making the efficiency of your machine increase. That is one of the most important jobs that every engineer has, increasing the efficiency of their machines. You can, of course, solve in this equation if you wanted to figure out the useful energy given by a machine of so-and-so efficiency. You can just pass this to multiply and pass this to divide. So how much useful energy does a machine with a 50% efficiency give if you put into it a total energy of, let's say, 100 joules. So if only 50% was useful, the useful energy will be 50% of 100, which is equal to 50 joules. Right? So that's just a way to use efficiency. Okay, so I'm going to erase this and we'll move on to power. So power is also something that you might hear about a lot, and maybe you don't really understand what it is. And many people confuse energy with power. But that's because they are similar, but they're not the same. So power, in Spanish potencia, is defined as the rate of doing work. So work is just the word for useful energy that we're using right now. But a rate means how fast it's going. So work divided by time. So the equation for power, which is called P, is going to be work over time. This is the definition of power as an equation, work over time. So how much work we did in how much time. So a machine is going to be more powerful if it did more work, and if it did that work in less time. So the less time it took, the more powerful it was. And this is actually what many machines cite. When you buy a refrigerator, when you buy a hair blower, it's going to give you its power in the box. you can find it because the unit is watts. So if you've ever heard of watts or vatios in Spanish, that is the unit for power. So what does that unit mean? What we have here is work, which is given in joules. Joules. And then we have over time, which is seconds. We always use time in seconds when calculating power. So if you have time in minutes or in hours, you need to convert it to seconds. So this means that the unit for power is joules per second. But this is also such a common unit that it has its own name. So this is called watt, with double T. And the letter is W, right? So let's do an example. You have a machine that does 50 joules of work every 2 seconds. Of work every 2 seconds. What is its power? So its power will be work over time. So 50 joules of work over 2 seconds of time, which gives us 25 joules per second, which is 25 watts. So you can put it as W, or you can put it as watt if you don't want to get confused with work, because it's confusing to have work and watt in the same problems. So you can leave it as watt to not get confused, or write vatios, the Spanish word for the unit. So that's a basic example of how to use this equation, and like with the efficiency equation, you can also turn it around to solve for something else. So if they tell you you have your hair blower says, your hair dryer says that it has a power of 1,000 watts. 1,000 watts. How much energy or how much work will it produce in 5 seconds? So 1,000 watts, 5 seconds. How much work does it do? So you solve for work here. You pass T to multiply, and you get that work is equal to power times time. So you do 1,000 watts times 5 seconds, which gives you 5,000 joules, right? Because work is in joules. So this is a way to use the equation too. And this also has another name. Maybe you've heard of watts and you've heard of kilowatts, kilowattios. Kilowatts just means 1,000 watts. So 1 kilowatt, which is written like this, is equal to 1,000 watts. Just like 1 kilogram is equal to 1,000 grams. So now the next time you are using or you are buying something, a blender, any machine, any electric device, you can look at it and see that it says watts or vatios, and you know it's talking about how powerful it is. And if it gives you joules, it's talking about how much energy it spends. So this watts is actually what you pay for when the light bill comes to your house. And the last thing that I wanted to say here is that sometimes it's useful to write this equation in a different way. So now we're going to use these two review equations that I told you. So let's see what this becomes. So we have the equation that power is equal to work over time. But we also know that work is defined as force times distance. So we can write here force times distance over time. And we can divide this fraction up, because when you multiply a fraction, you can divide it. So this is the same as force times distance over time. And distance over time was given here as speed. So this is also force times speed. So another equation of power that you can use, which means the same thing but is written in a different way, is that power is force times speed. So you might get some examples in the worksheet today that talk about something moving at a constant speed, and you can find the force, maybe the force of gravity or the weight that it has acting on it. If they ask you for the power and you have speed, you can use this version of the equation. Plug in the speed, plug in the force, and you'll get the power without having to know the work or the time. So that's another way to use power. And that's it for power and efficiency.